through a little presentation on sizing solar domestic hot water systems in commercial as well as residential applications that we've done at Viessmann here since about 1975. So we've got quite a bit of experience as far as solar thermal goes. And the objectives that we're going to roll through here today will be to list the necessary information needed to size domestic hot water systems using solar energy. We're also going to explain the differences between sizing a conventional domestic hot water system versus when we're trying to size out a collector array for a solar domestic hot water system to back up that conventional domestic system. And also to understand the tools to design a solar domestic hot water system for discussion purposes. So a lot of this, the reason why I put this presentation together was to enable you as the contractors or engineers, consultants, when you are looking at a potential project and solar does come up, or you mention it now that you got the confidence after going through this webinar, to have a look at possibly sizing a system, very simply, just for discussion purposes. And it's not for, to get the interest, the ball rolling with potential decision makers and owners, et cetera, so that we can, take that to Viessmann, for instance. We have a system here I'll review with you at the end, where we can actually put that into a simulation, give you a more firmed up quote and some information on that system. And like I say, this is really about getting that conversation started out there, and some familiarity with how these systems are sized and dimensioned, et cetera. So without going into too much detail, it's all in the presentation here. The first thing is about information. So what type bits and pieces of information should we gather when we are going to size a domestic hot water system using solar thermal? And for a number of years here now, we've developed this solar checklist, which is on our website, either the Viessmann US website or the Canadian website for Viessmann. We have a checklist that you can download. It's in an Excel spreadsheet file as well, or in a PDF form like this, which is writable. And information about the project is always good to have, because a lot of times you might be looking at a potential project. It might not happen for 2 years, but if we have all that detail as far as the contact information and project information, we can easily pull that up in our data, upload update the pricing, and resend that system quote back out to you. So that information is always helpful. I have done ones in the past where it's like 2 collector system or something like that, and then the guy comes back 2 years later and it's like, remember that quote we did? And it's we'd have to redo the whole project back over again. So it's good to have the detail, so we know what project is moving forward, and if we have to make any changes or adjustments as we move. Obviously, collector placement. So what room do we have for the collectors? So if we're sizing a system out and you only have room for 2 collectors, we're not trying to send a quote for 10 collectors. So it's really good to know limitations on roof or wall mount or ground mount, that sort of thing. And all that detail can be put in that little bottom left-hand area that I've kind of highlighted and put collector placement in. Also mechanical room information. So pipe runs, so supply and return connections between where the potential collector array might be sitting and the piping to the mechanical room where the tanks, et cetera, your mechanical system is going to be installed, to make sure that we can size things like, the amount of fluid we're going to need, diameter, the pipe sizes, all that kind of stuff will be detailed. Anything existing or proposed in this, if it's a new home or a new building that's being constructed, but what has been proposed as far as whether a direct fire tank for domestic, or if it's an indirect tank with a size or volume of that tank, as well as the boiler or the burner size of that direct fired hot water heater, whatever it might be that you're installing in there. So we get a pretty good idea of what we're going to be connecting to or possibly connecting to, as well as like dimensions of the room, et cetera. And, some information on the domestic hot water load is in there as well. How much domestic hot water we're going to be needing per day. And we're going to cover that here in a moment. And then finally, down the very bottom, we've got some information on just If you want to add some extra notes in there about, things like such as shading possibly, or, the roof is, 20 years old, that sort of stuff is always good to kind of add in there. And this little sheet will also cover things like pool heating and, backup spacing support. But this program or this presentation is really we're not going to dip into those applications. We're going to stick with the solar domestic hot water heating for the duration here. So site considerations. So when I show up on a site for solar, it's like, hey, where are we going to put the collectors? So I get a dimension on that. Things like, if it's a pitched roof or a slope roof, we're going to be installing these collectors on. What is the pitch of that roof? That's going to be the angle of the collectors to the horizon. So we need to know if that's a 412 pitch, a 512 pitch, or a 112 pitch. What that roof pitch is. If we're doing wall mount, ground mount, or flat roof mounting, obviously areas there, but you can kind of see what possible fixing kits we have available here at Viessmann, where we can do multiple installations based on the area that you want to put those collectors, so you kind of get an idea of what we have available here. Where that mechanical room is, also, if the roof is going to be, replaced in 2 years, it might not be the best time to, install that system. Maybe wait till the roof is replaced, and at that time integrate the bracketing and all that kind of stuff into the roof, and make that installation a little bit easier. And obviously, also we're looking at 25 or 30 years of life expectancy on these systems, so we want that whatever it's being attached to have that type of life cycle as well. So kind of covering all that stuff. And then you see the little compass here on the right hand side, and really solar works very effectively, solar thermal. When we are even, due south is obviously best. So those south facing roofs are desirable. But even 45 degrees, off east or west there, you're only losing about 5% of your total annual radiation that's going to hit those collectors. So it's a good idea that we know where those collectors are sitting. If you're a little bit 45 degrees, west here, you're going to get more solar radiation at the collectors in the afternoon. If I was east, obviously it's going to be more radiation at the collectors when the sun is rising in the morning. So that's why you only lose a small percentage of the actual total amount if it was facing due south here. So just some idea where that's going to be facing is always a good idea. We don't really like to size systems that are facing north. There's really not much radiation insulation is going to hit that collector, so we wouldn't advise that. But in this wheelhouse here is really where you get your ideal amount of radiation, just to cover that off. And of course, shading, it's hard, to get your crystal ball out here, but thinking about the 25 to 30 years of life cycle, those trees that are sitting out there on the horizon, will they impede that solar moving forward? Is this in Langley here, for instance, there's a talk of a high density construction happening here for more housing because of the housing shortage here. And so high rises are starting to be contemplated here, and multiples of those. We've seen some examples already of a couple of high rises being built here in Langley. So if you're in a high density area, if there's some proposals, we're going to be seeing some high buildings being built around that home. Is that going to be an issue? Those sort of things. We're kind of looking at that. We need to know if there's going to be any shading, because that will obviously impact the the potential of that solar thermal system. So looking at that and getting an idea of where that roof placement is and if they will be a problem. And you got to think about the time of year you're there. So if I'm there in December, and that roof could be heavily shaded during the December months, but in June and July, when that angle of that sun is a little bit different, we're gonna have a nice clear, unimpeded sun hitting that roof there. So the idea is obviously the time of year you're at the site as well might have an impact on the amount of shading on that roof that we're looking at here in the picture. And it's a good idea to get there actually are devices available. There's one that's that you can essentially outline the area that you're going to propose to install the system, and it will actually give you a 365-day a year type of idea of how much shading could be potential at this particular site. Solar Pathfinder, if you want to look that up, is what I'm talking about. So a very simple little device that you can use. It doesn't require a whole lot of technology, but I think there is an app that they've built for it now that you can utilize. But essentially, it's a fairly simple device to use. But we're kind of looking at that morning to early morning to kind of mid-afternoon time there to make sure that that site's not going to have a whole lot of shading throughout the year. So just some information there on that. We're looking at that 365 days a year as far as operation, but really the months that we're really kind of keying in on would be from somewhere around April to October, say, is kind of the months that are critical for solar thermal, at least in the more northern climates. As you get a little closer to the equator, there really isn't very little difference between January and July as far as their operation, other than you might have some rainy seasons, etc. But as far as the tilt there, it makes a little bit less importance. So in order to size this solar array that you see here in the red outline, this context, and this is a system here where we call it a preheat system, where you might have an existing tank with a boiler heating that tank up, and there's your domestic hot water coming out. We're going to supplement that boiler, try to keep that gas from firing here into that unit to heat that tank up. And what we're going to do is we're going to preheat the water. It's going to add another tank, as you see here, a little external heat exchanger. That could also be an internal heat exchanger. In this example, we have an external heat exchanger and 2 pumps. And so we're going to heat this tank up. It could either be up to set point of what the standby tank here is looking for, so that when we open up this fixture, that water's already at the temperature. That's going to leave the boiler off. Or it could be heated up to a temperature, that's still below the set point of the standby tank, but the boiler has to do less work now because we've already heated up that mass of water that's going to go into that standby tank. And the important thing here, just to note as well, is that, when it comes to solar thermal, it's very important that you have dedicated solar storage. So a dedicated battery, essentially, that when the sun is out, that tank there is totally available for the solar to dump that energy into that tank. Trying to tie the solar into an existing standby tank that the boiler is heating, you're going to have a very low efficient system because the temperature of that collector has to rise now because this tank is going to be hotter because the boiler is going to heat it. And also you have more risks of this system overheating, that sort of thing. So that dedicated storage is very important for solar thermal. But in order for us to know how to size this array and that tank up, we need to know how much domestic hot water is being utilized in that building. So whether it's a residence or an apartment building, how much water are we using here at what temperature for heating for hot water? And to get an idea of that will help us size what this needs to be over here as far as what we're sitting on the roof or on the ground. And of course, the battery of that volume of tank that we need to add into that system to make sure that we cover that off adequately. So another system here, this would be more of a newer system. We call this a bivalent tank or double coil tank. So you have a bottom coil and a top coil. The boiler heats up the top coil. It can't heat the bottom of that tank. So in this system here, as long as we don't recirc that bottom, mix that tank up with a recirc pump, the bottom of this tank would always be available as far as solar storage goes. And in the summer months, that whole tank could be heated by that solar collector. So it's just a different system look here, but same kind of goals in mind. So we see here that the tank, we have 225 liters per day of domestic hot water use. That's 54 degrees C. How do we get that information? In this application, we show you that we're using a water meter, and that meter is essentially in line in this case, and right to the tank. So there's no other, we're just measuring the cold water that's going into the domestic hot water tank. So as we use our water here for showering or washing dishes, whatever it might be, that tank is being reheated. And of course, we're getting a measurement of the amount of cold water going into this tank to be heated up for hot water. So we're not looking at the whole domestic hot water or domestic consumption of the building, adding in cold and hot water. We want to be specific here that we're only metering out what's going to the hot water tank here in this little application. There are also ones that are not invasive like this that you have to cut into your system. They're called ultrasonic flow meters. There's some rules of engagement on those as far as installation. You have to have some straight runs of pipe, etc. But again, the most accurate way to get an idea of how much hot water you're using per day in your site, and the more accurate this is, the more accurate this calculation is going to be as far as the solar collector array. the metering out or understanding or knowing how much water we have here with using metering is going to give you the most accurate calculation here as far as that goes. So we've done a lot of projects, the last couple of years where we put meters on and got a really accurate load here. And the assumption was previous to metering, the load was actually calculated about 3 times higher versus what the actual usage was. So what's the implication of that occurring when we oversize the domestic hot water load? Typically what's going to happen is we're not going to be able to sell that system because the collector array is going to be so large in comparison to, it's always in percentage of the amount of domestic hot water you're using. So the bigger that domestic hot water load is going to be, the bigger that solar array is going to be. So the more expensive that quote's going to get. So if I've got a system that's only using 5,000 gallons per day, but our rough estimations without, actual knowledge is, 15,000 gallons a day, that system's going to be 3 times larger than it needs to be. And what's going to happen is we're going to quote it and it's going to be too expensive, or it's going to be installed and it's going to overheat and they're going to have some problems there. So obviously this is a really important piece of the puzzle, and metering is the most accurate as far as that information. We could also look at summer gas consumption and get an idea, or if it's oil, what the oil consumption is, or that sort of thing. Or if you got electric meter on your electric water heater, get an idea of what that's kind of, how many kilowatts electric water heater is burning in the summertime, and separate from your electric bills, obviously. But this way here, as long as the boiler here is the only thing operating in the summertime to heat that domestic hot water tank up, you'll get a pretty accurate idea of what that domestic hot water load is going to be. But if you've got like a gas-fired stove and you got a gas-fired dryer in that building, if you got some, other auxiliary loads that are using that gas, you'll have to try to discount that load from the actual domestic hot water load here. So this works quite well when the boiler here is the only thing that's running in the summertime to heat the tank up. But if you have other loads there, it's going to be a little bit more of a challenge for you to get a really good idea of what that total volume is going to be here on that side. So another idea there. As far as estimations go, Viessmann's been doing this since about 1975 in Europe and in North America here, and so we have developed some rules of thumb as far as residential homes. 8 to 16 gallons of domestic hot water per day per person at 140 Fahrenheit. In multi-unit residences, that would be, a little bit lower because you tend to have a little bit more of a variance in multi-unit buildings than you do in, single detached dwellings, for instance, or, single family homes. So the known quantity of people there may vary quite a bit in multi-units. So we tend to drop that load per person per day down a little bit. So instead of 8 to 16, it's usually about 5 to 10 gallons per person per day in those buildings at 60 degrees Celsius. So if you don't give us a number, we can give you a rough calculation here using some rules of thumb on this side. And we'll use these numbers in a moment here to actually size an array up as we move through. And then again, if it's not a domestic hot water being used in a kind of a multifamily or detached dwelling or single family dwelling, if it's a car wash or laundromat or restaurant, offices, you could do the same sort of thing. We have average number of cars washed, and the capacity of the the nozzles, spray nozzles, et cetera, at that car wash, we can get a really good idea of what that number is going to be and the temperature of that water that they're using to wash the cars. Same thing with the laundromats. We get the washer machines there and what they're looking for as far as temperature to wash the clothes, as well as their amount of water they use per wash, for instance. And again, with restaurants, it's going to be the dishwashers, et cetera, that are on site there and how much water they're going to use per day there. And offices typically are going to be hot water consumption. There might be some showers there, et cetera. Gyms, the same sort of thing. Hospitals, same kind of idea as far as that goes. Number of people, patients, and hot water usage. So lots of good rules of thumb that we can use there, and a myriad of different applications where buildings are using hot water for their requirements. So from here, we've got the just like information about gathering and some rules of thumb there that you can use to get a good picture of what that system might look like before we actually get it installed. So that gives us all really good detail if you gather that information. But a lot of times what I end up with is this as far as a domestic hot water load when we're trying to calculate the solar thermal. And I just want to cover that this is not an accurate bit of information when we're sizing solar. So if I'm looking at a boiler and I'm going to install this in a building, an apartment building, for instance, we see here, and I want to size out the tank and that boiler size for my building, I could use ASHRAE's, average hourly demand method. There's a couple other methods that you can use here as well. This particular method here is really good because it varies a bunch of different types of applications you can see here as far as buildings go. But what this is going to, what you're trying to calculate here is the peak load of that building, and the boiler and that tank volume have to be of that size enough that when that peak load occurs, that we're not running out of hot water. So when we use this type of method, what we're really doing is we're trying to track and find out the peak area here. Where is the most hot water requirement in that particular building going to be? And of course, I'm going to size my tank, my standby tank, and my boiler or my direct fired tanks or electric water heat, whatever it might be that you're using there for domestic hot water production. I'm going to size it to make sure I cover off this big load right here. When I use this number and try to average it out over a 24-hour period, it's going to oversize that system again, just like we had just talked about there earlier. So this is usually when we end up with that, we're only using 5,000 gallons of water per day, but I'm going to use this, average hourly demand, and that's going to essentially oversize it. You're probably going to get somewhere around 15,000 gallons a day as far as your usage. So it's not really an accurate number for solar thermal applications. So instead, what we're trying to do with solar is look at it over that 24-hour period. And then we have, of course, we've got our solar radiation here, the amount of time we can actually harvest the solar. And what we want to try to do is size the collector array and the storage volume so that we can maximize the amount of harvesting we get, solar radiation we gather as energy, put into a tank to cover as much as 24-hour demand as possible, even though we're kind of constrained by that, 9 o'clock in the morning to, 5:30 at night type of time that we can actually heat that water up. So this is a more accurate idea. And that's why we kind of look at those rules of thumb and some of the other things we're looking at there, because we're really interested in this 24-hour demand, not so much about that peak, hour. So our goal is there to, make sure we have the collectors sized, and of course, we size this tank for solar so that we can, get as much energy as possible stuffed in that tank, and we can use that throughout the whole day instead of just, the whole 24-hour period, I should say, versus just, during those periods of time that people are using it while the sun is out there shining. And what we're trying to do here, obviously, is, if we fall short of that, and we got a collector array we sized up here, and of course we undersize the storage. What's going to happen is at some point in the day, the tank for our solar is going to heat up. It's going to shut the tank, essentially shut the pump off between the tank and the solar collectors. And now we have potential now where we're going to, the sun's still shining. There's a potential there that we're going to overheat these collectors, and we're going to go into a steam back system or some other particular problem. So it's always important to match the volume of this tank with a number of collectors so that we go through this whole period of operation without this tank actually reaching or achieving its set point and shutting that system off. Or if it does achieve the set point, we cool it down very quickly with a draw of hot water from the building. We cool that tank back down again. So it again, that pump kicks right back in again, and we don't have any situations where we're going into an overheat condition. So important to match those two together as far as that system goes. And again, like I say, it's we're going to talk a little bit about overheating here in a moment, but we're really trying to avoid this little period of time. It does reduce the efficiency of the system overall. It tends to be more service and more costly kind of repairs, et cetera, throughout the life cycle of the collectors when we undersize the storage on these systems. So we'll give you some rules of thumb here as well on that. So if we were looking at a residential application, we would want to make sure we had about 40 gallons of storage for every collector that we put up there on the roof, which is what it equates to as far as our Viessmann collectors go. And in commercial applications, that drops down a few gallons, between 22 and 31 gallons, because you're going to draw that water a little bit more, a little bit more consistently at a commercial application than in a residential application. The tank can be a little bit smaller in these commercial projects than it has to be in a residential project there. So it's just, again, some rules of thumb we have available for you to size those tanks up for that conversation you're going to have with that potential customer of yours. As far as the collector area goes, historically, when we talk about sizing solar thermal, we look at these two little lines on this graph here. The SF stands for solar fraction, and solar fraction is essentially the total energy supplied by the solar divided by the total amount of energy required. So it's essentially of the total amount of energy I need to heat my domestic hot water on an annual basis or a monthly basis, whatever it's going to be, the solar is going to cover this percentage of that. So that free energy, and the boiler has to cover off, or that direct fire tank has to cover off the whatever's left over after the solar fraction. The SE, or the system efficiency, means that the total amount of energy hitting that collector surface area, how much is actually being directed into that tank as usable energy, and how much is just being lost through heat loss through the collector, through the piping, etc., of the system. And the goal was always to kind of hit the intersection point. So this little green area that you see on the graph was our target with our collectors. So we have some webinars on the our VitoSol 200 FM Therm Protect coating, which talks about the coating actually changes to an emitter from an absorber as it heats up. So as far as overheating and issues like that, we tend to have a little less problems with the 200 FM and their lower temperatures to begin with. So we tend to oversize the system, give you a little bit more solar fraction. Our efficiency drops here a little bit because of that, but we could cover more of your daily domestic hot water load here, which is obviously going to be beneficial. Reduce your gas consumption, your carbon, your CO2 footprint, all that good stuff. Because of the Therm Protect, we can, add another collector or two collectors should that be desirable, and we can do that safely without having to add things like heat dumps and all that kind of stuff into your system. So it tends to keep the cost of those systems down than what they were, years ago when we didn't have this Therm Protect offering for you. Now we do. So the Therm Protect there comes in handy. We can size those systems a little bit larger, but we also have these other little rules of thumb that are in our system design guide manual. So if I was looking at a residential application and we had a 200 liters per day or 53 gallons of hot water per day that we were using in this residence, and we were targeting a 60% solar fraction, that would tell me, if we go over here, that 5 square meters of surface area of collector is what we're looking for, which is about 2 of our collectors put into a system. You see that up in the top right-hand corner. And those 2 collectors in this, residence at 53 gallons per day is going to cover about, 60% of their domestic hot water energy on an annual basis in this. So really, again, really good things for discussion purposes here. We have the same ones for commercial applications. So we look at, 1,585, 6,000 liters or 1,585 gallons of domestic hot water per day in this building. We don't have this shows, it's a little bit older. It shows the tubes as B and the flat plates as A. We still have tubes in Europe. It's not part of our product offering currently in North America. So just to kind of ignore the B over there, we're going to look at focus on the A, the flat plate collector here. So as we go over, you can see that amount of domestic hot water is going to be, somewhere around 350 kilowatt hours of energy requirement for this building for the domestic hot water usage. And we would need about 100 square meters or 1,076 square feet of surface area. So our scale you see on the top right is going to be much larger now, more collector surface area for this larger load to cover off again that percentage of domestic hot water in their building. So it's just good rules of thumb there that we can look at again, just to size out a system that we for a prospective client. Our system has got the guidelines. All the information that I am kind of reviewing with you guys here today is based off of this little manual that's available on our website. so in Canada and in the US. And there's little calculations in there as well. If you want to kind of size out a system for 100% of the domestic hot water requirement during whatever that month you're going to size this at, and I would always recommend we do this in the summertime, like July or August, the peak months. This manual will give you all of this information on how to do this. This little, it looks intimidating, but it really isn't all that intimidating formula once you kind of get used to it and you get all the inputs. So we need to know, obviously, the number of collectors to meet 100% of the domestic hot water load in this building would be the number of days in the month that you're selecting, the number of people occupying that home or building, the volume that we're going to use there. So again, it goes to that 50 to 70 liters per day for residential application, or, it was like 20 to 30, I believe, or sorry, 30 to 50 liters per day for a commercial application. The density of water at kilogram per liter, or 8.3 pounds per gallon. Specific heat capacity of the water, which is there in joules per kilogram. Delta T, so the cold water coming in and how hot you want that water to get to. The efficiency of the collector, and we give you that at 0.42, 42%. And the global radiation at that specific location of your space. So we have in the manual, we give you a bunch of areas here in Canada. In the US, we have even more locations, obviously, for all the different states. And you can use that number there. We give you from January right to December here, and you pick the month, and you're going to plot that number in here. So I used Toronto. You'll see that in a moment. And of course, the collector absorber area, which is going to be 2.32 square meters for the Vitasol 200 FM. So Toronto, Ontario, Canada, we see is at 22.3 megajoules per square meter per day, and we put that in there. I'm not going to go through the longhand of all this. I just plotted all those numbers in here, so you can see that we come up with a number here of 1.93. We round it up to 2. So 2 collectors in this home will cover off 100% of their domestic hot water requirements in the month of July. In December, if we were sizing this for December, that could be 10 collectors or 12 collectors or something like that. And of course, when we come down to July now, we would have to do something with that heat. Otherwise, we'd be oversizing the system here. So if we're at 100% capacity here in July, our number in December at 2 collectors might only be like 10%, but we're not oversizing the system. And it's a really good way, a method of sizing this out as well. So just a little bit of math there for you early in the morning here or mid-afternoon, wherever you might be. And then again, when we start looking at just some idea of like if you have this number of collectors on your in that system, kind of a recommended size tank for that dedicated solar thermal storage, and we're using indirect tanks here with the with their internal coils here, so you can see 1 to 2 people. That's a collector on the roof, and a 42 or 53 gallon tank, depending on how we're on the higher or lower end of that domestic hot water usage. We go all the ways up to 5+ people in that home. You're up to 3 collectors on the roof, and you're into a 120 gallon storage tank for your solar thermal. So it just scales up as your demand or load scales up with it. In commercial, we show, usually you're not going to have a battery of tanks. It's possible, but usually you go to a larger single tank, put an external heat exchanger in here as an example. So the solar is connected to one side, that the heat exchanger. The other side, we're gonna have another pump, and we're gonna flow the potable fluid that's in the storage tank through the other side here, pulling the heat off of that heat exchanger and dumping it in our storage tank. So if we had 20 people, 760 liters per day of domestic hot water usage, that would be a 265 gallon tank or 1,000 liter tank that we would throw in there. All the way up to 60 people in a unit. You're at 30 collectors now. And of course, that storage volume is now, up to a factor of 3 here, 3 times larger, 3,000 liters as far as the volume that we're looking for there. So some just good rules of thumb for you to kind of look at. Again, going back to the solar checklist here, that information could now, if you get that party interested in, well, let's, firm up those prices and see what that looks like as far as install cost. We'd be more than happy to take that solar checklist from you, put that into a simulation. And this is kind of an example of a simulation I did a year or so ago for a hotel in Saskatoon, a 30 collector system. And you can see, the amount of gas and cubic meters that you're going to offset, or propane, or, fuel oil here. The solar fraction is a little over 30% in this application on an annual basis. We see the efficiency of the system. Also, how many kilograms of CO2, carbon dioxide, we offset by not burning the fuel here, as an example. And we see, the volume of tank that we're going to need, and of course the number of collectors here in this little system. So it gives you a really good snapshot. And this is the other side of it, where we can show you a kind of more visual. The orange here is a total amount of energy needed for that domestic hot water usage. And this is the solar, and the yellow here, what it's going to cover on an annual basis. You see the peaks here in July as it peters off a little bit, in those winter months, and it kind of rises back up again starting in March. We start to peak again in April and May during those operations. So it gives you a good idea of what that system potentially can do before it's even installed in that application. So that's just, hopefully that was of use and interesting to you folks that joined us today. Just to kind of review those objectives, we've listed the necessary information needed, showed you that solar checklist, and all that information on, the site visits and shading, all that stuff, to size that domestic hot water system, explain the differences in the critical distributing, sizing a conventional system for domestic hot water versus a solar domestic hot water system, and then some of the tools that we have available to design that system, that solar design guide that can give you some really quick rules of thumb to get that discussion started. And then the ability of Viessmann to take that from a discussion, firm that information up for you through some solar simulations and some quoting, and hopefully turn those, those negotiations and discussions into a PO and into installation on that roof or wall or on the ground, wherever it might be. How are the questions? Any questions we got out there?
How do you like to integrate with hydronics?
Would that be
Something like a solar
for,
injection.
yeah, solar injection? It's possibly space heating, maybe on the backup on space heating. Typically with domestic hot water consumption, we're directly connecting to a storage tank and having that dedicated storage. So not really an injection system so much. If we get into more integration with a backup heat source, so we have a couple of methods there that we can work at. The solar preheat tank, for instance, that's the kind of where we have that dedicated tank. We flow out of that tank into the standby tank that the boiler or the direct fire tank is that's actually feeding the hot water to the building. Or you could do a dual coil type of application. But usually when we start getting into space heating backup, we might look at things like maybe a diverting valve versus injection. So if we always monitor the return temperature from the heating system, and that return temperature going back to the boiler drops down below whatever's stored in your tank. What we can do is take a diverting valve and essentially divert the incoming water to go through a coil of an indirect tank that the solar fluid's sitting in, and heating that water up before it goes back into the boiler. So now it's kind of heating that water up a bit. So the boiler has to do a little less work on that side. So I've seen some injection systems too, where we just essentially pipe and kind of inject on the primary loop, say of a boiler, for instance, inject into the return of that. And so essentially the boiler has a little less work to do. Sometimes we even inject on the supply side if there's a primary, secondary, so that we affect the system supply temperature versus the boiler temperature. So there's a couple of ways of doing it. It just depends on what your application is, and how much space you have is a big one, obviously, and what the goals are. I will mention, like I say, domestic hot water space heating. The better application there really is typically going to be your evacuated tube systems, because they have a much better R value when it comes to winter operation. You're going to lose less heat out of a evacuated tube than you will out of the solar thermal flat plate collectors. We have done some backup heating here on the west coast of Canada, but our design temperatures are we don't get some areas much less lower than about 10 degrees Celsius. So they tend to have a pretty decent operation effect. But if I'm going to, northern, you know, Alberta or something like that, I'm probably going to be looking at evacuated tubes for a backup space heating system. But for domestic hot water, flat plates are really effective year round um, for that usage. So I hope that answers the question. It was kind of a little bit of a rant there, but it also, I tried to cover a few little other things there as well. I guess we'll let you guys go. Have a good day.